Before we go on to general, potentially complicated regions, let's consider triangles first, which are constructed by these circles on the sphere. They are called great circles, which are the curves formed by intersecting the sphere with an equatorial plane passing through the center. There is a very nice way of finding the area of such a spherical triangle, which is related to the angles of the triangle. We start off with just the surface area of the entire sphere, and I'm going to assume that you probably know that the surface area is 4 pi for a unit sphere. Now consider the area enclosed by two great circles. If the angle made between these two great circles is alpha, then we can expect the area enclosed is computed like this. 4 pi is the area of the whole sphere, and alpha over 2 pi is the proportion of the angle occupied. So instead of the 2 pi angle at the point of intersection, we only take a slice of angle alpha. So the proportion of the area is alpha over 2 pi. So the surface area for this shape is 2 alpha. When we add one more great circle to the mix, there are more regions to consider, but we can use symmetry. For example, there is a spherical triangle in front right now, but on the back there is the exact same shape. Very similarly, these regions occur in pairs and have exactly the same shape by symmetry. Here, I color two regions the same if they have the same shape and area, and assume they have areas A, B, C, and D respectively. Because each shape appears twice on the sphere, twice the sum of A, B, C, D will give us 4 pi, 4 pi being the surface area of the whole sphere. Equivalently, A plus B plus C plus D equals 2 pi. On the other hand, if we now only focus on only two regions, A and C, they form an area enclosed by just two great circles. This is exactly the situation we dealt with a minute ago. If the angle between these great circles is alpha, then the area enclosed is 2 alpha. So the sum of A and C is 2 alpha. In exactly the same way, if we combine the regions A and D together, and the angle at the vertex is beta, then we have the sum of these areas to be 2 beta. Combining A and B together, then the sum of A and B is 2 gamma, where gamma is the angle at this vertex. All these relations between A, B, C, and D can then be aggregated here, and we can solve for A, the spherical triangle we are focusing on. To solve for A, we can first add up these three equations and subtract the first equation from it. This gives 2A equals 2 alpha plus 2 beta plus 2 gamma minus 2 pi, and dividing by 2, we get the area to be alpha plus beta plus gamma minus pi. The first part is like adding up the interior angles of the spherical triangle, and pi, or 180 degrees, is the angle sum of a triangle on a normal flat plane. For this reason, this quantity is called the spherical excess. How much additional angle is there? Given this formula for spherical triangles, we can already compute the area for a general region. The idea is that even if the boundary is not a part of a great circle, which here I deliberately take it not to be, we can still approximate it by a bunch of arcs of great circles. There are two arcs here, but even if I zoom in a lot, you still might not be able to see the difference between the yellow arcs and the original pink region. In any case, after approximating any region by arcs of great circles, we can dissect the result into several spherical triangles, and for each of them, we know how to find the area using the angles. Using more and more of these great circle arcs, it eventually approaches the region we started off with, so we are able to find the area of a general region on a sphere.